Hello and welcome to the Midnight Lab. Before we begin tonight's journey, take a moment to like the video and subscribe if you enjoy calm explorations of science, space, and the quiet mechanics of the universe. And while you're settling in, I'd love to know where you're watching or listening from tonight. Are you under city lights somewhere deep in the countryside, maybe near the ocean, or perhaps on the other side of the planet entirely? Wherever you are, something rather extraordinary is happening beneath you right now. Because even if your room feels perfectly still, even if the ground beneath your feet feels solid and unmoving, the place you're sitting is actually moving at incredible speeds. At this very moment, the Earth beneath you is spinning. It's also orbiting the Sun. The Sun itself is travelling through the Milky Way galaxy, and the galaxy is drifting through the wider universe. In other words, wherever you're listening from tonight, that location is not staying in one place for very long. But the motion doesn't stop there. Deep below the surface, continents are slowly drifting apart. Far beneath that, currents of hot rock are rising and sinking inside the mantle. At the planet's centre, vast rivers of molten metal swirl and churn, generating a magnetic shield that protects life on the surface. Meanwhile, the oceans are circulating across the globe in immense planetary loops. The atmosphere is constantly flowing around the planet in waves of wind and weather. Even the axis of Earth itself gently wobbles, almost like a spinning top. Our planet, it turns out, refuses to stay still. And yet, most of the time we never notice. Human beings evolved to experience the world from a very particular frame of reference. From our perspective, the ground feels stable, the horizon feels fixed, and the sky appears to move around us. But when we step back and look at the deeper physics of our world, a very different picture emerges. Earth is not a quiet, motionless sphere. It is a layered system of motion where gravity, heat, rotation, and cosmic forces combine to create a planet that is constantly shifting, circulating, and evolving. Tonight, we're going to take a slow and careful journey through those motions. We'll travel back billions of years to the spinning cloud of dust that formed our planet. We'll explore the subtle physics that keeps Earth rotating day after day. We'll dive beneath the crust to see how continents drift across the surface, and we'll step outward into space to see how our entire solar system is carried through the galaxy. Along the way, we'll discover that the reason Earth refuses to stay still isn't chaos, it's physics. Quiet, patient, beautifully predictable physics that has been shaping this planet for more than 4.5 billion years. So wherever you're watching from tonight, whether it's midnight, early morning, or somewhere in between, settle in, get comfortable, and let your mind drift for a while. Because the ground beneath you may feel still, but in reality, you're riding on a world that has never stopped moving. If you pause for a moment and simply notice the space around you, the world feels remarkably calm. The floor beneath you seems steady, the walls do not sway, the chair you are sitting on appears perfectly still. Nothing in your immediate surroundings suggests that you are moving at all, and yet, at this very moment, you are travelling through space at speeds that would be difficult to imagine if you could actually feel them. The ground beneath you is rotating as part of a spinning planet. The entire planet is moving in an enormous path around the Sun. The Sun itself is circling the centre of the Milky Way galaxy. And the galaxy, in turn, drifts through the wider universe among countless others. All of this motion is happening continuously, but we feel none of it. This quiet illusion of stillness is one of the most remarkable features of living on Earth. Our senses are not designed to detect steady motion when everything around us moves together. Instead, they respond primarily to changes in motion, sudden accelerations, shifts in direction, or vibrations that break the uniform rhythm of movement. If you ride in a smooth train that has already reached its cruising speed, the interior of the carriage feels motionless. Only when the train slows down, speeds up, or turns do you notice the movement again. The same principle applies to the entire planet. Because every object around you is moving along with Earth, your body has no simple reference point against which to detect the motion. The trees, the buildings, the air, the oceans, and even the atmosphere are all participating in the same vast movement. To your senses, it feels like standing still. Understanding this illusion requires a concept that physicists call a frame of reference. A frame of reference is simply the perspective from which motion is measured. If you are sitting in a moving train, you appear stationary relative to the seat beside you. but relative to the landscape outside the window, you are racing across the countryside. In the late 19th and early 20th centuries, the French mathematician and physicist Henri Poincaré explored this idea in depth. Poincaré emphasized that motion cannot be defined in absolute terms without choosing a frame of reference first. From one viewpoint, an object may appear stationary, while from another it may be moving rapidly. This insight helps explain why Earth's enormous motion feels invisible. From the perspective of the cosmos, our planet is a dynamic object moving through space at remarkable speeds. But from the perspective of someone standing on the ground, the entire surrounding world is moving together, creating the experience of perfect stillness. This realization did not come easily to human civilization. For most of recorded history, people assumed that Earth stood at the center of the universe, unmoving while the sun, moon, and stars circled above it. The daily rising and setting of the sun seemed to confirm this idea. If the heavens moved across the sky, then surely the Earth beneath our feet must be stationary. Yet some thinkers began to question that assumption surprisingly early. In the 14th century, the French philosopher Nicole Rem proposed that the apparent motion of the stars could be explained if Earth itself were rotating. Oresme argued that the movement of the heavens might simply be an illusion created by the motion of our own planet. His suggestion was remarkably bold for its time. However, it would take another 2 centuries before the idea of a moving Earth gained serious traction. In the 16th century, the Polish astronomer Nicholas Copernicus proposed a model in which the Sun occupied the center of the planetary system, with Earth orbiting around it. Copernicus did not possess telescopes powerful enough to observe all the evidence that would later support his theory. But his model solved several puzzling patterns in planetary motion that had troubled astronomers for centuries. Gradually, the idea that Earth was not the stationary center of everything began to spread. Later observations by scientists such as Galileo Galilei, Johannes Kepler, and Isaac Newton provided stronger and stronger confirmation that our planet was indeed moving through space. Once this realization took hold, an even deeper question emerged. If Earth is moving, how many kinds of motion are actually happening at once? The answer turns out to be surprisingly complex. The first and most familiar motion is rotation. Earth spins around an imaginary line called its axis. One complete rotation takes roughly 24 hours, producing the cycle of day and night. At the equator, the surface of the planet is moving at a speed of about 1,600 km per hour as it turns. And yet, because everything on the surface rotates together, that motion remains imperceptible. At the same time, Earth is traveling in a wide orbit around the Sun. This path takes approximately 365 days to complete. The speed of this orbital journey is about 30 kilometers per second. To put that into perspective, if a commercial airplane could travel that fast, it would cross the Atlantic Ocean in less than 2 minutes. But even this enormous speed is not the end of the story. The entire solar system, including Earth, is moving through the Milky Way galaxy. Our Sun follows a vast orbit around the galactic center at roughly 220 kilometers per second. Completing one full circuit of the galaxy takes around 230 million years. That means the last time the solar system was in its current position within the galaxy, dinosaurs had not yet appeared on Earth, and the layers of motion do not stop there. The continents beneath our feet are slowly shifting as part of a process called plate tectonics. Deep inside the mantle, hot rock circulates in slow convection currents, gradually rearranging the surface of the planet over millions of years. The oceans are also moving, circulating heat and salt through enormous currents that span the globe. The atmosphere flows constantly around the planet in patterns of wind and weather. Even Earth's axis is not perfectly fixed. It wobbles gently over long periods of time, a phenomenon known as axial precession. Our planet is not merely moving in one way, it is moving in many ways at once. In the late 19th century, the Austrian physicist Ernst Mach proposed an intriguing idea about motion itself. Mach suggested that the inertia of objects, their resistance to changes in motion, might be connected to the distribution of mass throughout the entire universe. This concept, often called Mach's principle, implies that motion cannot be understood in isolation. The behavior of objects here on Earth may be linked in subtle ways to the presence of distant stars and galaxies. Although Mach's principle remains a subject of debate among physicists, the idea highlights something important. Our planet does not exist as an isolated object drifting alone in space. It is part of a vast interconnected system shaped by gravity, energy, and motion on scales far beyond our everyday experience. When viewed from this broader perspective, the stillness we feel on Earth begins to look very different. The calm ground beneath our feet is actually part of a planet that spins, orbits, circulates, shifts, and travels through space. The reason we experience stillness is not because motion is absent. It is because every part of our immediate world participates in that motion together. The air moves with the planet. The oceans move with the planet. Our bodies move with the planet. We are passengers on a world that never truly stops. And once you begin to see Earth in this way, the idea of a motionless planet quietly fades. In its place appears something far more interesting. A living dynamic world defined not by stillness, but by movement on every scale imaginable. To understand why Earth spins today, we need to travel far back in time, long before the planet itself existed. The story begins in a region of space that looked nothing like the familiar solar system we know today. Instead of planets, moons, and a bright central star, there was a vast cloud of gas and dust drifting quietly through one of the spiral arms of the Milky Way galaxy. Astronomers call such a structure a molecular cloud. These clouds are enormous. Some stretch across many dozens of light years and contain enough material to form thousands of stars. They are made mostly of hydrogen gas, with smaller amounts of helium and trace elements such as carbon, oxygen, silicon, and iron. Mixed within the gas are tiny solid grains of dust, often no larger than smoke particles. For long periods of time, these clouds remain stable. Gravity tries to pull the material inward, while internal pressure from the gas resists collapse. But occasionally something disturbs the balance. A nearby supernova explosion can send shockwaves through the cloud, or the slow movement of the cloud through the galaxy can cause regions of higher density to form. Eventually, one region within this enormous cloud begins to collapse under its own gravity. This collapse marks the beginning of the process that would eventually create the Sun, Earth, and every other planet in the solar system. As gravity pulls the gas inward, the material does not fall straight toward the center. Almost nothing in space is perfectly motionless. Even a tiny amount of initial rotation within the cloud becomes important as the collapse begins. Here, a fundamental physical principle comes into play, known as the conservation of angular momentum. Angular momentum describes how rotation behaves in a physical system. When a rotating system contracts, its rotation speeds up. A simple way to visualize this effect is by watching a figure skater spin on ice. When the skater pulls their arms inward, their rotation becomes noticeably faster. The same principle applies on a cosmic scale. As the collapsing cloud shrinks, its rotation accelerates. Instead of forming a perfectly spherical shape, the material flattens into a spinning disk surrounding a dense central region. Astronomers call this structure a protoplanetary disk. At the center of this disk, gravity compresses gas until temperatures and pressures become extreme. Eventually, nuclear fusion ignites, and a young star is born. That star becomes our Sun. The remaining material in the surrounding disk continues to orbit the newborn star in a broad, rotating sheet of gas, ice, and dust. Long before modern telescopes could observe these disks directly, some thinkers had already imagined such a process. In the 18th century, the philosopher Immanuel Kant proposed that the solar system formed from a rotating cloud of matter that gradually collapsed under gravity. A few decades later, the French mathematician Pierre-Simon Laplace developed a similar concept in greater detail. Their proposal became known as the nebula hypothesis. At the time, the idea was largely speculative. Astronomers did not yet possess instruments capable of observing young planetary systems forming around distant stars. But over the centuries that followed, the hypothesis proved remarkably accurate. Modern telescopes now routinely observe protoplanetary disks around young stars scattered throughout our galaxy. One of the most powerful instruments used for this purpose is the Atacama Large Millimeter Submillimeter Array, usually shortened to ALMA. This observatory sits high in the Atacama Desert in northern Chile, where the dry atmosphere allows astronomers to detect faint signals from coal dust and gas in distant star systems. Images from ALMA reveal swirling disks filled with rings, gaps, and spiral structures where planets are forming. These observations provide a direct glimpse into the kind of environment that once surrounded the young Sun. Inside such a disk, the process of planet formation begins with something surprisingly small. Tiny grains of dust collide gently with one another as they orbit the star. At first, these collisions are delicate. Electrostatic forces allow the particles to stick together, forming slightly larger clumps. Over time, these clumps grow into pebbles, then into objects measuring meters across, and eventually into bodies kilometers wide. These early building blocks of planets are called planetesimals. The detailed physics of this stage was explored extensively by the Soviet planetary scientist Viktor Safronov during the 20th century. Safronov developed a theory describing how gravitational interactions between planetesimals cause them to collide and merge, gradually building larger planetary embryos. According to Safronov's model, once objects grow large enough, their gravity begins to dominate the local environment. Smaller bodies are pulled inward and collide with them at increasing speeds. Through countless impacts, these growing worlds accumulate more and more mass. This process, known as planetary accretion, continues for millions of years. In the early solar system, the environment was far from peaceful. Planetary embryos frequently collided with one another in enormous impacts that reshaped their structure. The young Earth itself likely experienced several massive collisions during this time. These violent encounters did more than simply add material to the growing planet. They also transferred energy and angular momentum. Every collision altered the way the young Earth rotated. Some impacts sped up its spin. Others may have tilted its axis or changed the direction of rotation. Over time, the combined effects of these events produced the spinning planet that would eventually stabilize into the Earth we know today. But collisions alone do not explain everything about the behavior of protoplanetary disks. Inside these disks, the gas and dust do not orbit smoothly forever. Instead, the disk gradually evolves as angular momentum moves outward through the system. Understanding how this transport happens puzzled astronomers for many years. One important breakthrough came from the astrophysicist Stephen Balbus and his collaborator John Hawley. In the early 1990s, they studied a phenomenon known as magnetorotational instability. This instability occurs when weak magnetic fields interact with rotating ionized gas in the disk. Under the right conditions, the magnetic fields link neighboring layers of gas together. As the inner material orbits slightly faster than the outer material, the magnetic connection causes angular momentum to move outward through the disk. This process creates turbulence and allows matter to spiral gradually toward the central star, while other material spreads outward. Although the details are mathematically complex, the result is simple to understand in principle. The disk does not remain perfectly smooth. It becomes a dynamic environment where swirling turbulence, magnetic forces, and gravitational interactions all shape the formation of planets. Within this rotating disk of dust and gas, the young Earth inherited its motion. The planet did not start spinning randomly after it formed. Instead, it was born inside a system that was already rotating. The entire protoplanetary disk was spinning around the Sun. Every fragment of material within it carried angular momentum from the original collapsing cloud. As the Earth assembled from countless collisions and mergers, it naturally retained part of that inherited rotation. The direction of Earth's spin, its speed, and its tilted axis all trace their origins back to those early conditions in the spinning disk surrounding the young Sun. In other words, the reason Earth rotates today is not because something continues to push it. It spins because it has been spinning ever since the solar system itself was born, and because space offers very little friction to slow it down. That ancient motion has persisted for billions of years. The quiet rotation of our planet, the steady rhythm of day and night, is a direct echo of a cosmic event that began more than 4.5 billion years ago. The spin we experience today is the lingering memory of a collapsing cloud of gas and dust that once began to turn. If a spinning object in space begins to rotate, a natural question soon follows. Why does it keep spinning? Here on Earth, motion often fades away. A rolling ball eventually slows down. A spinning top gradually wobbles and falls. A bicycle coasts to a stop once the rider stops pedaling. Friction with the ground and resistance from the air steadily remove energy from the system. But space is very different. In the vast emptiness between planets, there is almost nothing to slow a rotating body down. There is no solid surface scraping against it, and almost no atmosphere to provide drag. As a result, once an object begins rotating in space, it tends to continue rotating for extremely long periods of time. The principle that governs this behavior is called the conservation of angular momentum. Angular momentum is the rotational equivalent of linear momentum. While linear momentum describes motion in a straight line, angular momentum describes motion around an axis. The fundamental idea is that in a system where no external torque is applied, the total angular momentum remains constant. In plain language, if nothing interferes with the rotating system, the rotation continues. This principle can be expressed through a simple relationship used in physics. Angular momentum equals the rotational inertia of an object multiplied by its angular velocity. Written out in words, the equation becomes angular momentum equals moment of inertia multiplied by angular velocity. The moment of inertia measures how mass is distributed around an axis of rotation, while angular velocity describes how quickly the object spins. For a planet such as Earth, this rotational momentum was inherited during its formation in the early solar system. Once the planet formed and began spinning, there was very little in the near vacuum of space capable of removing that rotational motion. So the rotation continued. The mathematical foundations for understanding rotational motion were developed in the 18th century by the Swiss mathematician and physicist Leonhard Euler. Euler introduced a set of equations known as Euler's equations of rigid body dynamics. These equations describe how rotating objects behave when forces act upon them. They apply to spinning satellites, rotating asteroids, and even planets. Euler's work revealed that rotation can be more complex than simply spinning around a perfectly stable axis. Depending on how mass is distributed within an object, the orientation of the rotation axis can shift slightly over time. These small changes produce subtle variations in the direction of the spin. A particularly elegant geometric interpretation of this behavior was later described by the French mathematician Louis Poinsot in the 19th century. Poinsot developed a visualization known as Poinsot motion, which helps explain how rotating bodies behave when no external forces are applied. In this model, the axis of rotation traces out a smooth path as the object spins, almost as though the rotating body were gently rolling along an invisible surface. For perfectly symmetrical objects, this motion is simple and stable. But when the mass distribution is uneven, the rotation can become more complicated. In extreme cases, a rotating object can tumble chaotically. This phenomenon is sometimes called the tennis racket effect, because if a tennis racket is tossed into the air spinning around certain axes, it will flip unpredictably during flight. Planets, fortunately, are usually much more stable than tennis rackets. Their large mass and roughly spherical shape allow them to maintain steady rotation over extremely long time scales. Still, the rotation of a planet does produce measurable physical effects. One of the most visible consequences of planetary rotation is something called equatorial bulging. When a planet spins, centrifugal effects cause material near the equator to move slightly outward. This outward push is not strong enough to tear the planet apart, but it does reshape the planet very subtly. Instead of forming a perfect sphere, a rotating planet becomes slightly flattened at the poles and slightly wider at the equator. This shape is known as an oblate spheroid. The mathematics describing this effect were studied in the 18th century by the Scottish mathematician Colin Maclaurin. Maclaurin analysed how rotating fluid bodies respond to the balance between gravity pulling inward and rotational forces pushing outward. His calculations showed that the faster a body rotates, the more pronounced this equatorial bulge becomes. Earth displays this effect clearly. The planet's equatorial diameter is about 43 kilometers larger than its polar diameter. That difference is small compared with the overall size of the planet, but it is large enough to be measured with modern instruments. Other planets show the effect even more dramatically. Jupiter, which rotates extremely rapidly, completes one rotation in roughly 10 hours. As a result, its equatorial bulge is far more pronounced, giving the giant planet a noticeably flattened appearance. Earth rotates more slowly, but the effect is still present. Despite the apparent stability of planetary rotation, it is not perfectly constant. In fact, scientists monitor the exact rate of Earth's spin with astonishing precision. One of the most powerful tools used for this purpose is a technique known as Very Long Baseline Interferometry, often abbreviated as VLBI. This method links radio telescopes across continents to observe distant quasars. Quasars are extremely bright and distant objects powered by supermassive black holes at the centers of galaxies. Because they lie billions of light years away, their apparent positions in the sky remain essentially fixed from Earth's perspective. By measuring the exact arrival times of radio signals from these quasars at different telescopes, scientists can determine the orientation and rotation of Earth with extraordinary accuracy. This global network of observatories allows researchers to measure tiny fluctuations in Earth's rotation that would otherwise be impossible to detect. Among the scientists who have studied these variations in detail is Richard Gross, a geophysicist at NASA's Jet Propulsion Laboratory. Gross and his colleagues analyze how changes within Earth systems affect the planet's spin. These changes can arise from many sources. Large earthquakes can slightly redistribute mass within the crust. Seasonal shifts in atmospheric winds can alter the distribution of air around the planet. Even the movement of water in oceans and melting ice sheets can produce subtle changes in rotational speed. These effects are extremely small. In many cases, they alter the length of a day by only a few milliseconds. Yet with modern measurement techniques, those tiny variations can be detected and studied. In fact, the length of a day on Earth is not exactly 24 hours. The precise duration fluctuates slightly over time due to the shifting movements of Earth's atmosphere, oceans, and interior. Over very long timescales, other forces also play a role. The gravitational pull of the Moon creates tidal friction in Earth's oceans. This process slowly transfers angular momentum from Earth to the Moon, gradually slowing Earth's rotation while causing the Moon to drift farther away. But the pace of this change is extremely slow. Hundreds of millions of years ago, a day on Earth may have lasted closer to 22 hours. Today it lasts 24 hours. In the distant future it will grow slightly longer still. For now, though, the planet's spin remains remarkably steady. Every sunrise and sunset we experience is a quiet reminder of a motion that began billions of years ago when the solar system itself was forming. Earth continues to rotate not because something keeps pushing it, but because the laws of physics allow that ancient motion to persist. In the stillness of our everyday lives, the entire planet quietly turns beneath us. If the Earth is constantly moving through space, another question naturally follows. Why does it move in the path that it does? Why does the planet circle the Sun rather than drifting away into the darkness of interstellar space, or spiraling inward until it falls into the star itself? The answer lies in one of the most profound and far-reaching ideas ever developed in science: gravity. Gravity is the force that governs the architecture of the solar system. It binds planets to stars, holds moons around planets, shapes galaxies, and determines the motion of objects across the universe. The modern understanding of gravity began to take shape in the late 17th century through the work of the English physicist and mathematician Isaac Newton. Newton proposed that every object with mass attracts every other object with mass. This attraction acts across distance and grows stronger when objects are heavier or closer together. He expressed this relationship in what became known as the law of universal gravitation. In words, the equation states, the gravitational force between two objects equals the gravitational constant, multiplied by the mass of the first object multiplied by the mass of the second object, divided by the square of the distance between them. Although the equation itself is simple, its implications are enormous. It means that the same force causing an apple to fall from a tree also governs the motion of planets around the Sun and moons around planets. Newton himself famously reflected on this connection. According to the popular story, he began thinking deeply about gravity after observing an apple fall in an orchard. Whether the apple story unfolded exactly as told is still debated by historians. What matters is the realization that the force pulling objects toward Earth also extends outward into space. Under Newton's theory, the Sun's immense mass creates a powerful gravitational pull. The planets, including Earth, are constantly being drawn toward it, but the planets are also moving sideways through space at tremendous speeds. These two motions combine to create an orbit. Instead of falling directly into the Sun, Earth continually falls sideways around it. The planet is perpetually pulled inward by gravity, yet its forward motion keeps it circling the star in a graceful path. The geometry of this motion was first described decades earlier by the German astronomer Johannes Kepler. Kepler worked with extremely precise astronomical observations collected by the Danish astronomer Tycho Brahe. Using this detailed data, Kepler discovered that the paths of planets were not perfect circles, as earlier astronomers had assumed. Instead, planets move along slightly stretched shapes called ellipses. This insight became the first of what are now known as Kepler's laws of planetary motion. Kepler's first law states that planets orbit the Sun in elliptical paths, with the Sun located at one focus of the ellipse. His second law explains how planets move along those paths. It states that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. In simpler terms, this means that planets move faster when they are closer to the Sun and slower when they are farther away. Kepler's third law connects the size of an orbit to the time it takes to complete it. The farther a planet lies from the Sun, the longer its orbital period becomes. These laws were remarkably accurate descriptions of planetary motion, even though Kepler did not yet know the physical force responsible for them. Newton's law of gravitation eventually provided that explanation. Together, the ideas of Kepler and Newton revealed that the solar system is governed by precise mathematical relationships. Planets do not wander randomly through space. Their paths follow predictable patterns shaped by gravity and motion, yet the gravitational structure of the solar system is more intricate than it might first appear. The gravitational pull of the Sun dominates the system, but every planet also exerts its own gravitational influence. These interactions create subtle but important effects. One fascinating example involves regions of space where gravitational forces balance in unusual ways. In the late 18th century, the Italian-French mathematician Joseph Louis Lagrange studied the three-body problem, which examines how three objects interact through gravity. Lagrange discovered that under certain conditions, there are special points in space where the gravitational forces of two large bodies and the orbital motion of a smaller object combine to create stable equilibrium. These locations are now called Lagrange points. In a system like the Earth and the Sun, there are 5 such points. At some of these points, an object can remain in a relatively stable position, orbiting the Sun in step with Earth, while maintaining a constant relationship with both bodies. Modern space missions often take advantage of these locations. For example, the James Webb Space Telescope operates near one of these gravitational balance points, allowing it to maintain a stable orbit while observing the distant universe. The existence of Lagrange points highlights the remarkable complexity of gravitational systems. Even in something as seemingly simple as the orbit of a planet, the underlying physics contains layers of subtle interaction. The solar system also exhibits behavior that is not perfectly predictable over extremely long periods of time. In the 20th century and into the present day, researchers began using powerful computers to simulate planetary orbits across millions or even billions of years. One of the scientists who has studied these long-term dynamics in detail is the French astronomer Jacques Lascar. Lascar discovered that while the solar system is largely stable, it also displays a degree of chaotic behavior over extremely long timescales. In this context, chaos does not mean disorder or destruction. Instead, it means that very small differences in initial conditions can gradually grow over time, making exact predictions increasingly difficult. For example, tiny gravitational interactions between planets can slowly alter the shape of their orbits. These changes are extremely gradual. They unfold over tens of millions or even hundreds of millions of years. For everyday human experience, the solar system appears perfectly stable. Yet from the perspective of deep time, the planetary system is a dynamic and evolving structure. Modern research institutions continue to study these complex gravitational interactions. One example is the Institut de Mécanique Céleste et de Calcul des Éphémérides in France. Scientists there perform detailed numerical simulations of planetary motion, calculating the positions of celestial bodies far into the future. These simulations help astronomers understand how planetary orbits change over time and how gravitational resonances between planets influence their long-term stability. Despite these intricate interactions, the overall structure of the solar system remains remarkably balanced. Earth's orbit around the Sun has persisted for more than 4.5 billion years. During that time, the planet has completed more than 4 billion journeys around its star. Each orbit takes approximately 365 days, and during every one of those days the planet continues its steady fall around the Sun. The motion is both simple and astonishing. A planet moves forward through space at about 30 kilometers per second, while gravity quietly bends its path into a continuous curve. From the ground beneath our feet, that immense journey feels completely invisible. But in reality, Earth is tracing a vast loop around the Sun year after year, guided by the silent influence of gravity. Our planet is not wandering through space alone. It is part of a carefully balanced gravitational system, where the pull of massive bodies and the momentum of motion combine to shape the architecture of the solar system. Look up at the night sky, and the moon appears calm and distant, quietly following its familiar path across the darkness. Yet the relationship between Earth and the moon is anything but passive. The two bodies are locked together in a continuous gravitational exchange that influences the oceans, alters the planet's rotation, and slowly reshapes their shared orbit. To understand that relationship, it helps to begin with the most widely accepted explanation for how the moon formed in the first place. For many years, scientists debated several competing ideas. Some proposed that the moon formed alongside Earth from the same material. Others suggested that it formed elsewhere and was later captured by Earth's gravity. But neither explanation fully matched the evidence gathered from lunar rocks, brought back by the Apollo missions during the late 1960s and early 1970s. Those samples revealed something curious. The chemical composition of the moon is extremely similar to the outer layers of Earth, especially in terms of oxygen isotopes. At the same time, the moon contains far less iron than Earth does, suggesting that the material forming the moon originated mostly from the outer regions of a larger body. To explain these observations, planetary scientists developed what is now known as the giant impact hypothesis. According to this model, the early Earth experienced a massive collision with a young planetary body roughly the size of Mars. This object has been given the name Theia, after a figure from Greek mythology associated with the moon. During the collision, an enormous amount of material was blasted into orbit around the Earth. Much of this debris consisted of molten rock and vaporized material from the outer layers of both bodies. Over time, gravity gathered that orbiting debris together, forming a new object. That object became the Moon. The giant impact model was refined in modern times by planetary scientists such as Robin Canup at the Southwest Research Institute. Canup and other researchers developed detailed computer simulations showing how such a collision could produce the correct mass and composition for the Earth-Moon system. Another scientist who helped expand this line of research is Sarah Stewart at the University of California. Stewart and her collaborators proposed that after a particularly energetic impact, the debris around Earth may have briefly formed an unusual structure known as a synestia. A synestia is a vast rotating cloud of vaporized rock shaped somewhat like a giant spinning donut. In this scenario, both Earth and the material that would become the Moon temporarily existed inside this enormous rotating structure, before gradually cooling and separating into two distinct bodies. Although the details of this stage are still being investigated, the key idea remains clear. The Moon was born from a violent collision early in the history of the solar system. Once the Moon formed, gravity bound it permanently to Earth. But their relationship is not as simple as one object circling another. In reality, both Earth and the Moon orbit around a shared point in space called a barycenter. A barycenter is the center of mass of a system containing two or more objects. In the case of Earth and the Moon, this point lies inside Earth itself, but not exactly at the center. Instead, the barycenter sits roughly 4,600 kilometers from the center of Earth, which places it beneath the surface, but still significantly offset. Because of this arrangement, the Earth does not remain perfectly stationary while the Moon orbits. Both bodies perform a subtle gravitational dance around their shared center of mass. This motion is small compared with the size of Earth, but it is real. If you could observe the planet from a distant vantage point in space, you would see Earth tracing a gentle wobble as the Moon circles around it. Gravity, however, does more than simply guide their orbits. It also stretches both bodies through a phenomenon known as tidal forces. Tidal forces arise because gravity weakens with distance. The side of Earth closest to the Moon experiences a slightly stronger gravitational pull than the center of the planet, while the far side experiences a slightly weaker pull. This difference in gravitational strength causes Earth to stretch slightly along the line connecting it to the Moon. The result is a pair of tidal bulges in Earth's oceans. One bulge forms on the side of Earth facing the Moon, where the Moon's gravity pulls ocean water outward. The other bulge forms on the opposite side, where the slightly weaker gravitational pull allows water to drift outward as well. As Earth rotates beneath these bulges, coastlines pass through regions of higher and lower water levels, producing the familiar rise and fall of the tides. The physics behind tidal motion was first analysed mathematically by Isaac Newton, who recognised that the same gravitational force responsible for planetary motion also governs tides on Earth. Later scientists expanded on Newton's work. Among them was the British physicist William Thomson, better known as Lord Kelvin. Kelvin developed mathematical models describing how tides propagate through oceans and interact with coastlines and ocean basins. Today, tidal behavior is studied by oceanographers around the world. Organizations such as the National Oceanic and Atmospheric Administration, often abbreviated as NOAA, operate extensive networks of tide gauges along coastlines. These instruments record sea level changes with remarkable precision, allowing scientists to track tides, storm surges, and long-term sea level trends. Satellite missions also measure the height of the ocean surface across the entire globe, revealing complex tidal patterns that move through the oceans like slow-moving waves. But the influence of tides does not stop at the shoreline. The continuous rise and fall of ocean water creates friction against the seafloor. This friction gradually converts a tiny amount of Earth's rotational energy into heat. Although the energy lost during a single day is extremely small, the effect accumulates over millions of years. The British mathematician George Darwin, son of the famous naturalist Charles Darwin, studied this process in the late 19th century. George Darwin developed the theory of tidal evolution, which describes how tidal friction transfers angular momentum from Earth to the Moon. As Earth's rotation slows slightly, the Moon gains energy and moves into a slightly higher orbit. Modern measurements using laser reflectors placed on the Moon during the Apollo missions confirm this process directly. Scientists bounce laser beams off these reflectors and measure the time it takes for the light to return. These experiments show that the Moon is currently drifting away from Earth at a rate of about 3.8 centimeters per year. That may not sound like much, but over geological timescales it becomes significant. Hundreds of millions of years ago, the Moon was noticeably closer to Earth. As a result, tides were stronger and the planet rotated somewhat faster. Over the course of Earth's long history, this quiet exchange of energy between Earth and the Moon has gradually reshaped the dynamics of the system. Today, the gravitational partnership between these two bodies continues to shape our world. The tides influence marine ecosystems, coastal environments, and ocean circulation. The presence of the Moon also stabilizes Earth's axial tilt, helping maintain relatively stable climate patterns over long periods of time. What appears in the night sky as a peaceful glowing disk is actually part of a complex gravitational relationship that began with a colossal collision billions of years ago. Ever since that moment, Earth and the Moon have remained linked together, circling their shared barycenter while slowly exchanging energy through the quiet rhythm of the tides. When we look across the surface of Earth, the planet appears solid and stable. Mountains rise from the ground, continents stretch across thousands of kilometers, and oceans fill vast basins that seem fixed in place. Yet beneath that familiar surface lies an interior that is anything but quiet. Deep inside the planet, immense amounts of heat continue to move, circulate, and slowly reshape the world above. To understand this hidden motion, it helps to picture Earth not as a single solid sphere, but as a layered structure built over billions of years. The outermost layer is called the crust. This is the thin shell of rock that forms the continents and the ocean floor. Compared with the overall size of the planet, the crust is surprisingly delicate. In some places beneath the oceans, it is only about 5 kilometers thick, while beneath large continents it can reach roughly 70 kilometers. If Earth were scaled down to the size of an apple, the crust would be thinner than the apple's skin. Beneath the crust lies a much thicker region known as the mantle. The mantle extends down to a depth of roughly 2,900 kilometers and makes up the majority of the planet's volume. Although the mantle is composed of solid rock, the temperatures and pressures within it are so extreme that the material behaves over long periods almost like a very slow-moving fluid. Below the mantle lies the outer core, a layer of molten metal composed mostly of iron and nickel. This region begins about 2,900 kilometers beneath the surface and extends to a depth of roughly 5,100 kilometers. Even deeper sits the inner core, a solid sphere of iron and nickel roughly the size of the Moon. Despite temperatures estimated to exceed 5,000 degrees Celsius, the immense pressure at Earth's center keeps this region solid. This layered structure was revealed through the science of seismology, the study of how earthquake waves travel through the planet. When earthquakes occur, they send vibrations through Earth's interior. By analyzing how those waves bend, reflect, and slow down, scientists can map the internal structure of the planet in remarkable detail. One important discovery came from the Danish seismologist Inge Lehmann in the 1930s. By carefully studying earthquake signals, Lehman concluded that Earth must contain a solid inner core inside the liquid outer core. Her insight helped complete the modern picture of the planet's deep interior. But knowing the structure of Earth raises another question. Why is the inside of the planet so hot? Part of the answer comes from the violent history of planetary formation. When Earth formed more than 4.5 billion years ago, countless collisions between planetesimals released enormous amounts of energy. Much of that energy was converted into heat and trapped inside the growing planet. Some of that primordial heat still remains today. However, another major source of heat continues to operate inside Earth even now. This source comes from radioactive decay. Certain elements within Earth's interior contain unstable atomic nuclei. Over time, these nuclei spontaneously break apart, releasing energy in the form of heat. Among the most important heat-producing elements are uranium, thorium, and potassium. The role of radioactive elements in Earth's history was studied extensively by geochemists during the 20th century. One of the most influential scientists in this field was Claire Patterson. Patterson is widely known for determining the age of Earth in the 1950s by measuring lead isotopes produced through uranium decay. His work revealed that the planet formed approximately 4.54 billion years ago, but the same radioactive processes used to measure that age also release heat deep inside the planet. That heat gradually flows outward toward the surface. Because rock is not an especially efficient conductor of heat, much of this energy moves through the mantle by a different process known as convection. Convection occurs when hot material rises while cooler material sinks. A familiar example can be seen when heating a pot of soup on a stove. The liquid at the bottom warms first and becomes less dense. As it rises, cooler liquid from above sinks downward to replace it, creating a slow circulating motion. Inside Earth's mantle, something similar happens, although on an enormous scale and over far longer times. Hot rock deep within the mantle slowly rises toward the surface. As it approaches the cooler upper layers, it gradually loses heat and begins to sink again. Over millions of years, this process creates vast convection currents circulating through the mantle. The movement is incredibly slow. In many places, mantle material may rise or sink at rates of only a few centimeters per year. Yet when these motions continue for millions of years, they become powerful forces capable of reshaping the planet's surface. The idea that the mantle circulates in this way was proposed during the early development of plate tectonics, but the details of how mantle motion operates are still being studied today. One important concept within this field is known as mantle plume theory. This idea was proposed in the 1970s by geophysicist W. Jason Morgan. Morgan suggested that in some regions, narrow columns of unusually hot mantle material rise from deep within the planet. These rising plumes can punch upward through the mantle and reach the base of the crust. When this happens, the intense heat may trigger volcanic activity at the surface. Certain volcanic chains, such as the Hawaiian Islands, are thought to form above long-lived mantle plumes. As a tectonic plate moves slowly across the surface of Earth, the plume continues to deliver magma upward, creating a chain of volcanoes that mark the plate's motion over time. This process reveals how deeply connected Earth's surface features are to events happening thousands of kilometers below. Studying such hidden structures requires sophisticated techniques. One of the most powerful tools used by geophysicists is seismic tomography. Seismic tomography works somewhat like a medical CT scan, but on a planetary scale. Instead of using X-rays to image the human body, scientists use seismic waves generated by earthquakes. These waves travel through Earth's interior at different speeds, depending on the temperature and composition of the material they pass through. By recording seismic signals at many locations around the world, researchers can reconstruct three-dimensional images of structures deep within the planet. Large international research efforts contribute to this work. One important organization involved in collecting seismic data is the Incorporated Research Institutions for Seismology, commonly known as IRIS. This consortium coordinates networks of seismic instruments around the world, allowing scientists to gather detailed measurements of earthquake waves. The resulting data have revealed enormous features inside Earth's mantle, including massive regions where hot material rises slowly upward from great depths. These deep currents of heat and rock are not merely geological curiosities, they are among the most important drivers of motion on our planet. Mantle convection helps power the movement of tectonic plates. It feeds volcanic eruptions that create new land and enrich the atmosphere with gases. It recycles material between Earth's surface and interior through subduction zones where oceanic crust sinks back into the mantle. Even the slow rearrangement of continents over millions of years can be traced back to heat rising from deep within the planet. In other words, the ground beneath our feet is not supported by a static interior. It rests on top of a planet whose deep layers are constantly circulating, slowly transferring heat outward toward the surface. Although these movements occur far below our daily experience, they are an essential part of Earth's ongoing evolution. Beneath the quiet landscapes of mountains, plains, and oceans lies a restless interior where heat continues to flow, driving the slow and steady processes that shape the world we live on. If the interior of Earth is slowly circulating with heat and motion, it raises a natural question about the planet's surface. Does the ground we walk on remain fixed in place, or is it also part of that deeper movement? For much of human history, the continents were assumed to be permanent and unmoving. Mountain ranges, coastlines, and oceans appeared stable on the timescales of everyday life. From a human perspective, landscapes seem eternal, but the deeper history of the planet tells a different story. Today, scientists understand that Earth's outer shell is divided into large moving sections called tectonic plates. These plates include both continents and portions of the ocean floor, and they slowly shift across the surface of the planet over millions of years. This framework is known as the theory of plate tectonics, one of the most important scientific discoveries of the 20th century. Plate tectonics unites several scientific fields, including geology, geophysics, and oceanography. Together, these disciplines reveal that the surface of Earth behaves not as a single unbroken shell, but as a mosaic of moving pieces. The plates float on top of the upper mantle, a region that is warm and capable of extremely slow deformation. Because of this, the plates can move gradually across the surface while interacting with one another along their boundaries. These interactions shape many of the dramatic features we see on Earth today. Mountain ranges rise where plates collide. Deep ocean trenches form where one plate sinks beneath another. Earthquakes occur when plates grind past each other, releasing built-up stress along faults. Yet this understanding of moving continents was not immediately accepted. In the early 20th century, the German scientist Alfred Wegener proposed a radical idea called continental drift. Wegener noticed that the shapes of certain continents appeared to fit together like pieces of a puzzle. The coastlines of South America and Africa, for example, seemed to match remarkably well when placed side by side. But Wegener did not stop at coastlines. He also examined fossils, rock formations, and ancient climate evidence found across different continents. Identical fossils of the prehistoric reptile Mesosaurus were discovered in both South America and Africa. Similar rock layers appeared on continents that are now separated by vast oceans. To Wegener, the most logical explanation was that these continents had once been joined together in a single supercontinent, which later broke apart and drifted across the surface of Earth. He called this ancient landmass Pangaea, meaning all lands. Wegener presented his ideas in 1912 and expanded them in a book published a few years later. Although his evidence was compelling, most scientists initially rejected the theory. The main problem was that Wegener could not explain how entire continents could move through solid ocean crust. Without a convincing mechanism, the idea seemed physically impossible. For several decades, the concept of continental drift remained controversial. The breakthrough came after the Second World War, when new technologies allowed scientists to explore the deep ocean floor in unprecedented detail. One of the key figures in this discovery was the American geologist and oceanographic cartographer Maury Tharp. Working at Columbia University in the 1950s, Tharp carefully analyzed sonar data collected by research ships crossing the Atlantic Ocean. Using this information, she produced detailed maps of the ocean floor. What she discovered was extraordinary. Running down the center of the Atlantic Ocean was a massive underwater mountain chain stretching thousands of kilometers. This feature, now known as the Mid-Atlantic Ridge, formed part of a global network of mid-ocean ridges encircling the planet. Tharp's maps also revealed a deep rift valley running along the crest of the ridge. This suggested that the ocean floor was splitting apart, with new crust forming as molten rock rose from the mantle below. At first, some of Tharp's colleagues hesitated to accept the implications of her work. But as additional data accumulated, the pattern became undeniable. The ocean floor was not static. It was slowly spreading outward from the ridges. This discovery provided the missing mechanism that Wegener had lacked. If new ocean crust forms at mid-ocean ridges and moves outward over time, then continents riding on tectonic plates could indeed drift across the planet. The theory of plate tectonics quickly took shape during the 1960s. Several scientists played important roles in developing the mathematical and physical framework behind the theory. Among them were the geophysicists Dan Mackenzie and John Tuzo Wilson. Mackenzie helped demonstrate how the motion of rigid plates on a spherical surface could explain patterns of earthquakes and volcanic activity around the world. Wilson introduced the concept of transform faults, which are plate boundaries where two plates slide horizontally past one another. Together, these insights revealed that Earth's surface is divided into several major tectonic plates, along with numerous smaller ones. Today, scientists recognize more than a dozen major plates, including the Pacific Plate, the North American Plate, the Eurasian Plate, and the African Plate. These plates move at speeds typically ranging from a few centimeters to about 10 centimeters per year. That rate may sound slow, but over millions of years it leads to enormous changes. A continent moving at 5 centimeters per year travels roughly 50 kilometers in a million years. Over 100 million years, that same continent could shift thousands of kilometers across the planet. The motion of tectonic plates is driven by several physical forces. One of the most important is called slab pull. In regions where oceanic plates sink into the mantle at subduction zones, the descending slab of dense crust pulls the rest of the plate behind it. Because oceanic crust becomes heavier as it cools, gravity helps drag the plate downward into the mantle. Another force is known as ridge push. At mid-ocean ridges, newly formed crust sits higher than the surrounding seafloor because it is still hot and buoyant. As this crust cools, gravity causes it to slide gradually downhill away from the ridge, pushing the plate outward. Together, slab pull and ridge push help keep tectonic plates in motion. Beneath them, the slow convection of the mantle provides additional movement and energy, linking surface tectonics to processes deep inside the planet. Modern technology now allows scientists to measure plate motion directly. Using networks of high-precision global positioning system, or GPS, receivers, researchers can track the positions of points on Earth's surface with millimeter-level accuracy. By monitoring these positions over time, scientists can observe continents drifting across the globe in real time. For example, measurements show that North America is slowly moving away from Europe as the Atlantic Ocean continues to widen. Meanwhile, the Pacific Plate is moving northwestward, carrying the Hawaiian Islands with it. Satellite geodesy, the science of measuring Earth's shape and motion using satellites, has confirmed that plate tectonics is an ongoing process happening right now. Although these movements occur far too slowly to notice in daily life, they are continuously reshaping the planet. Over the span of hundreds of millions of years, continents assemble into supercontinents and later break apart again. Oceans open and close. Mountain ranges rise and eventually erode away. The ground beneath our feet may feel stable and permanent, but in geological terms it is part of a surface that never truly stands still. The continents are passengers on enormous tectonic plates, slowly drifting across the face of a restless planet, powered by heat, rising from deep within its interior. If the continents slowly drift across the planet today, it means their present arrangement is only a temporary moment in a much longer story. Over the vast stretches of geological time, the surface of Earth has rearranged itself again and again. Oceans have opened and closed, landmasses have merged together and then separated once more. The familiar map of the modern world represents only a brief snapshot in a planet that has been reshaping its surface for billions of years. One of the most striking patterns revealed by geological research is the repeated formation of supercontinents. A supercontinent is exactly what the name suggests, a massive landmass formed when most or all of Earth's continents gather together into a single connected body of land. The most famous example is Pangaea, the supercontinent that existed during the late Paleozoic and early Mesozoic eras. Around 300 million years ago, nearly all of Earth's major land masses were joined together into one enormous continent surrounded by a global ocean called Panthalassa. If you could have travelled back in time to that ancient world, you might have walked for thousands of kilometres without encountering an ocean. But Pangaea was not the first supercontinent. Geological evidence suggests that several others existed long before it. One of these ancient landmasses is known as Rodinia, which assembled roughly 1 billion years ago. Rodinia eventually broke apart around 750 million years ago, triggering dramatic changes in Earth's oceans and climate. Even earlier still was a supercontinent called Columbia, sometimes also referred to as Nuna. Columbia existed approximately 1.8 billion years ago and may have remained stable for several hundred million years before fragmenting. These repeated cycles of continental assembly and breakup are sometimes described as the supercontinent cycle. Over intervals of several hundred million years, tectonic forces gradually pull continents together into large clusters and later tear them apart again. Understanding these ancient configurations requires creative detective work. Rocks do not come with labels telling geologists where they originally formed. Instead, scientists must piece together clues preserved within the rocks themselves. One of the most powerful tools for doing this is a technique known as paleomagnetism. Paleomagnetism studies the ancient magnetic signatures locked inside certain rocks. When molten rock cools and solidifies, tiny crystals containing iron can align themselves with the direction of Earth's magnetic field. Once the rock hardens, that alignment becomes permanently frozen in place. These magnetic orientations act like tiny compasses preserved in stone. By measuring the direction of magnetization in ancient rocks, scientists can determine where those rocks were located relative to Earth's magnetic poles when they formed. One of the pioneers of this method was the British geophysicist Stanley Runcorn during the 1950s. Runcorn and his colleagues studied magnetic patterns preserved in rocks from Europe and North America. Their results revealed something remarkable. The magnetic directions suggested that the continents had not remained in fixed positions. Instead, the data made far more sense if the continents themselves had shifted across the surface of Earth. This evidence provided some of the strongest early confirmation that continental drift was real. Over time, paleomagnetic research expanded across the globe. By combining data from many different regions, geologists began reconstructing maps of ancient continental arrangements stretching hundreds of millions of years into the past. Another scientist who contributed significantly to understanding these ancient worlds is the Canadian-American geologist Paul Hoffman. Hoffman's research focused on the geology of ancient continents and the dramatic environmental changes that accompanied their movements. One of the most fascinating periods he studied involves the breakup of Rodinia, which may have played a role in triggering one of the most extreme climate events in Earth's history. This event is known as Snowball Earth. According to the Snowball Earth hypothesis, large portions of the planet may have been covered in ice during certain intervals roughly 700 million years ago. Geological evidence suggests that glaciers reached regions near the equator, indicating that the planet may have been nearly frozen from pole to pole. Although the exact details remain debated, many scientists believe that continental positions influence these climate extremes. When continents cluster together near the equator, they can alter ocean circulation and atmospheric patterns in ways that affect the planet's temperature. This highlights an important point. The movement of continents does not only reshape coastlines and mountain ranges, it also influences the climate of the entire planet. When continents break apart, new ocean basins form between them. These oceans allow currents to circulate heat around the globe in different ways. At the same time, the creation of mountain ranges during continental collisions can alter wind patterns and rainfall. Even the long-term balance of carbon dioxide in the atmosphere can be affected by continental movement. For example, when mountains rise during tectonic collisions, fresh rock becomes exposed to weathering. Chemical reactions between rainwater and rock gradually remove carbon dioxide from the atmosphere, which can contribute to long-term cooling of the planet. In this way, tectonic activity connects deep Earth processes with the climate experienced at the surface. Reconstructing these ancient continental arrangements has become increasingly sophisticated with modern technology. Today, geologists use specialized software tools that allow them to digitally rotate continents backward through time based on geological and geophysical data. One widely used system is called G-Plates, an open-source software platform developed through collaborations between several research institutions. G-Plates allow scientists to combine multiple types of information, including paleomagnetic data, fossil distributions, and seafloor spreading records. Using these inputs, researchers can build animated models showing how continents have moved across the planet during the past several hundred million years. Watching such reconstructions unfold can feel almost like observing the slow choreography of a planetary dance. Africa drifts northward toward Europe. India races across the Indian Ocean before colliding with Asia and raising the Himalayas. The Atlantic Ocean gradually widens as North America and Europe move apart. The timescales involved are so vast that the motion appears almost frozen when measured against human lifetimes. Yet the movement never truly stops. Every year the continents shift by a few centimetres. Over millions of years, those small changes accumulate into transformations that reshape the geography of the entire world. The continents we recognise today will not remain arranged in their present positions forever. Hundreds of millions of years from now, tectonic forces will likely gather them together once again into a new supercontinent. The exact configuration of that future landmass remains uncertain, but the pattern of assembly and separation seems to be a recurring feature of Earth's geological history. What feels permanent on human timescales is actually part of a slow and ongoing journey. The continents beneath our feet are travellers moving across the surface of a restless planet, guided by forces deep within Earth's interior and unfolding across the immense canvas of geological time. Far beneath the continents, below the shifting tectonic plates and the slow circulation of the mantle, lies one of the most extraordinary regions of our planet. At a depth of nearly 3,000 kilometres, the character of Earth changes dramatically. Solid rock gives way to an immense ocean of molten metal. This region is known as the outer core, and it surrounds a dense central sphere called the inner core. Together they form the deepest and most mysterious parts of the planet. For many centuries, no one knew what existed at such depths. Direct exploration is impossible. Even the deepest human-made drill holes reach only a few kilometres beneath the surface, barely scratching the outermost layers of the crust. Yet scientists have managed to map the deep interior of Earth using an ingenious method. They listen to earthquakes. When a large earthquake occurs, it releases powerful waves of energy that travel through the entire planet. These seismic waves move through different materials in different ways. Some waves travel easily through solid rock but cannot pass through liquids. Others slow down or bend depending on the density of the material they encounter. By studying how these waves arrive at seismometers around the world, researchers can reconstruct the structure of Earth's interior. One of the most important discoveries in this field came from the Danish seismologist Inge Lehmann in 1936. Lehmann carefully analysed seismic data from earthquakes and noticed that certain waves behaved in ways that could not be explained if Earth's core were entirely liquid. Her conclusion was bold and elegant. She proposed that the core must contain a solid inner sphere surrounded by a liquid outer layer. Subsequent research confirmed her insight. Today scientists understand that the outer core is a vast shell of molten iron and nickel, extending from roughly 2,900 kilometres beneath the surface down to about 5,100 kilometres. Below that lies the inner core, a solid ball of iron and nickel roughly 1,200 kilometres in radius. Temperatures within the core are extraordinary, estimated to exceed 5,000 degrees Celsius. That is comparable to the surface temperature of the Sun. Despite this intense heat, the inner core remains solid because the pressure at Earth's centre is immense. The weight of the entire planet presses inward, forcing the iron atoms into a tightly packed crystalline structure. The outer core, however, remains liquid, and this ocean of molten metal is not still, it moves. Within the outer core, heat rising from deeper regions drives slow but powerful convection currents. Hot liquid iron rises toward the top of the core, cools slightly, and then sinks again in a continuous cycle. At the same time, Earth itself is rotating. When electrically conductive fluid moves within a rotating environment, something remarkable happens. The motion can generate magnetic fields. This process is known as the geodynamo. The geodynamo theory explains how Earth produces its global magnetic field, the invisible force that guides compass needles and shields the planet from dangerous radiation. One of the key scientists who helped develop this theory was the physicist Walter Elsasser during the middle of the 20th century. Elsasser proposed that the movement of electrically conductive fluid in the outer core could act as a natural generator. As molten iron circulates and twists within the rotating planet, it creates complex electrical currents. Those currents, in turn, generate magnetic fields. The interaction between fluid motion, electrical conductivity, and planetary rotation sustains Earth's magnetic field over long periods of time. The process is somewhat similar to how a mechanical generator produces electricity. In a power plant, spinning coils of wire move through magnetic fields to generate electric current. Inside Earth, the process works in reverse. Moving liquid metal generates electric currents, and those currents produce magnetic fields. The result is a vast magnetic structure surrounding the entire planet. This magnetic field extends far out into space, forming a protective region known as the magnetosphere. The magnetosphere deflects charged particles streaming outward from the Sun in a flow called the solar wind. Without this protection, energetic particles could strip away the atmosphere over long periods of time, as appears to have happened on Mars. These particles can also damage biological molecules and disrupt electronic systems. Instead, Earth's magnetic field acts as a kind of invisible shield. Most incoming charged particles are redirected around the planet. Some become trapped in regions known as the Van Allen radiation belts, while others spiral along magnetic field lines toward the polar regions. When these particles collide with gases in the upper atmosphere, they create the shimmering lights known as auroras, visible in the skies near the Arctic and Antarctic. The magnetic field, however, is not perfectly constant. Over long stretches of time, its strength and orientation change. In fact, the polarity of Earth's magnetic field occasionally reverses completely. During such an event, the magnetic north and south poles swap positions. Evidence for these geomagnetic reversals is preserved in the ocean floor. As molten rock rises at mid-ocean ridges and cools to form new crust, iron minerals within the rock align themselves with the direction of Earth's magnetic field at that moment. Once the rock solidifies, the magnetic orientation becomes locked in place. Because new crust forms continuously at these ridges, the seafloor contains a layered record of past magnetic fields. Bands of rock show alternating patterns of normal and reversed magnetization, forming symmetrical stripes on either side of mid-ocean ridges. This pattern was first recognized during studies of seafloor magnetism in the 1960s, and it provided crucial evidence supporting the theory of plate tectonics. Today, scientists continue to monitor Earth's magnetic field using networks of observatories spread across the globe. One such network is Intermagnet, an international consortium of magnetic observatories that measure changes in the planet's magnetic field with great precision. These instruments record small fluctuations caused by processes both within Earth's core and in near-Earth space. The data help researchers understand how the geodynamo evolves over time. Although magnetic reversals have occurred many times in Earth's history, they unfold slowly, typically over thousands of years. The last major reversal, known as the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. At present, Earth's magnetic field continues to fluctuate, but there is no immediate indication that a reversal is about to occur. What remains clear is that the churning metal within Earth's outer core plays a vital role in sustaining the planet's magnetic shield. Deep beneath the surface, far beyond the reach of direct observation, rivers of molten iron circulate through the outer core. Their motion generates electric currents. Those currents create the magnetic field that surrounds and protects our world, and all of it unfolds silently beneath our feet, hidden within the depths of a planet whose interior remains in constant motion. If you stand beside the ocean and watch the water, the motion you notice first is usually the surface. Waves roll toward the shore, tides slowly raise and lower the sea level. Wind pushes ripples across the water. All of this movement is easy to see, but the most powerful motion of the oceans is hidden far below the surface. Across the entire planet, the oceans participate in a slow and immense circulation system that connects every major basin. Water moves through this system not over days or months, but over centuries and even thousands of years. Oceanographers often describe this vast circulation as the global ocean conveyor, though the scientific term for it is thermohaline circulation. The name thermohaline comes from two key properties of seawater: temperature and salinity. Temperature refers to how warm or cold the water is, while salinity describes how much dissolved salt the water contains. Together, temperature and salinity determine the density of seawater. Colder water tends to be denser than warmer water. Saltier water is also denser than fresher water. When density differences develop within the oceans, gravity causes denser water to sink while lighter water rises. This simple physical principle drives the large-scale circulation of the world's oceans. One of the scientists who made major contributions to understanding these processes was the American oceanographer Henry Stommel during the middle of the 20th century. Stommel studied how variations in temperature, salinity, and Earth's rotation influence ocean currents. His theoretical work helped explain why certain large currents follow stable paths across the oceans rather than dispersing randomly. Among the most famous examples is the Gulf Stream, a powerful current that carries warm water from the Gulf of Mexico across the North Atlantic Ocean. The Gulf Stream plays an important role in shaping climate, particularly in Europe. Because the current transports heat northward, regions such as the British Isles experience milder winters than other areas at similar latitudes. But surface currents like the Gulf Stream represent only part of the global circulation. The deeper engine of thermohaline circulation begins in some of the coldest regions of the planet. In the North Atlantic Ocean and around Antarctica, seawater can become extremely dense. Cold temperatures remove heat from the water, while the formation of sea ice leaves behind highly concentrated salt. When seawater becomes dense enough, it sinks toward the deep ocean. This process is known as deep water formation. In the North Atlantic, particularly near Greenland and Iceland, dense water sinks to great depths and begins flowing southward along the ocean floor. Similar processes occur in the Southern Ocean surrounding Antarctica. The water that sinks in these regions begins a slow journey through the deepest layers of the world's oceans. Over time, this cold deep water spreads into the Atlantic, Indian, and Pacific basins. Eventually it rises again through a combination of mixing processes and upwelling currents closer to the surface. Once near the surface, the water can warm again and continue its circulation. The full cycle of thermohaline circulation may take roughly 1,000 years to complete. That means some of the water currently flowing through the deep Pacific Ocean may have last been at the surface when medieval civilizations were flourishing. Understanding these immense ocean movements has required both theoretical insight and decades of careful observation. Another influential scientist in the study of large-scale ocean circulation is the physical oceanographer Carl Wunsch of the Massachusetts Institute of Technology. Wunsch has spent much of his career examining how ocean currents interact with atmospheric winds, Earth's rotation, and the shape of the ocean basins. His work has shown that ocean circulation cannot be understood as a simple conveyor belt alone. Instead, the system is a complex network of interacting currents, mixing processes, and feedback loops. Modern technology now allows researchers to monitor these movements with remarkable precision. One of the most important observational programs in oceanography today is the Argo Float Network. Argo consists of thousands of autonomous instruments drifting throughout the world's oceans. Each float periodically descends hundreds or even thousands of meters below the surface, measuring temperature and salinity as it travels. After collecting its data, the float rises back to the surface and transmits its measurements to satellites before beginning another cycle. Together, these instruments create a detailed global picture of how heat and salt move through the oceans. Another powerful tool for studying ocean motion comes from satellites that measure the height of the ocean surface. Through a technique called satellite altimetry, instruments aboard satellites send radar signals toward the ocean and measure the time it takes for the signal to bounce back. Because ocean currents slightly raise or lower the sea surface, these measurements allow scientists to map large-scale currents across entire ocean basins. These observations reveal that the oceans are constantly moving in patterns shaped by wind, temperature, salinity, and the rotation of Earth. The consequences of this circulation are enormous. The oceans store vast amounts of heat from the sun. By transporting that heat around the planet, they help regulate global climate. Without ocean circulation, temperature differences between the equator and the poles would likely be far more extreme. Marine ecosystems also depend on these movements. Upwelling currents bring nutrient-rich water from the deep ocean toward the surface, feeding plankton and supporting complex food webs that include fish, seabirds, and marine mammals. Even the chemistry of the atmosphere is influenced by ocean circulation. The oceans absorb large amounts of carbon dioxide from the air. As water moves through the deep circulation system, that carbon can remain stored in the ocean for centuries. In this way, the motion of the oceans plays a crucial role in regulating the balance of gases in Earth's atmosphere. All of this activity unfolds quietly beneath the surface. From the shoreline, the sea may appear calm, its waves rising and falling with a gentle rhythm. But far below, immense currents carry water across entire oceans, linking distant regions of the planet through slow and continuous motion. The oceans, like the continents and the mantle beneath them, are part of a world that never truly rests. They are constantly circulating, redistributing heat, nutrients, and energy across the surface of a moving planet. Above the oceans and continents lies another vast system of motion that is just as dynamic as the currents of the sea or the drifting of tectonic plates. This system is the atmosphere. Earth's atmosphere is a thin envelope of gases extending upward from the surface for hundreds of kilometers. Most of the air we breathe, however, is concentrated within the lowest layer, known as the troposphere, which reaches roughly 12 kilometers above the ground on average. Although the atmosphere may seem light and delicate compared with the solid planet beneath it, its mass is enormous. The total weight of Earth's atmosphere is estimated to be about 5 quadrillion metric tons. That immense volume of air is constantly moving, circulating around the planet in response to sunlight, rotation, and temperature differences. The large-scale patterns governing this motion are described by atmospheric circulation models. One of the scientists who played a central role in developing these models was the Norwegian meteorologist Wilhelm Bjerknes during the early 20th century. Bjerknes recognized that the atmosphere behaves as a fluid governed by the laws of physics. He proposed that weather and atmospheric motion could be predicted by applying mathematical equations describing fluid dynamics and thermodynamics. His work helped transform meteorology from a largely descriptive science into a quantitative discipline. In simple terms, atmospheric circulation begins with an imbalance in how the sun heats the planet. Near the equator, sunlight arrives almost directly overhead for much of the year. This intense solar energy warms the surface and the air above it. Warm air becomes less dense than cooler air, causing it to rise. As this air rises, it expands and cools, eventually spreading outward at high altitudes. Farther away from the equator, the air begins to descend again as it cools and becomes denser. This rising and sinking motion creates enormous circulation loops in the atmosphere. One of the most prominent of these loops is known as the Hadley cell, which transports heat from the equatorial regions toward the subtropics. Additional circulation cells operate at higher latitudes, forming a complex system that redistributes heat around the globe. However, the motion of air on a rotating planet is not straightforward. Because Earth is spinning, moving air masses do not travel in perfectly straight lines. Instead, their paths appear to curve as they move across the surface. This effect is known as the Coriolis effect. The Coriolis effect arises because different parts of Earth's surface move at different speeds as the planet rotates. Near the equator, the surface travels faster as it sweeps through space, while regions closer to the poles move more slowly. When air moves from one latitude to another, it carries its original rotational speed with it. This difference causes the air to appear deflected relative to the ground. In the northern hemisphere, moving air tends to curve toward the right. In the southern hemisphere, it curves toward the left. This deflection plays a major role in shaping the prevailing wind patterns of the planet, including the trade winds and the powerful mid-latitude westerlies. It also influences the rotation of large storm systems. The Coriolis effect is responsible for the spinning motion of hurricanes and cyclones, although it is worth noting that it does not determine the direction of water draining in a household sink. That popular myth survives mostly because it sounds entertaining, but the effect is far too small to control your kitchen plumbing. Beyond these basic wind patterns, the atmosphere also contains large-scale undulating structures known as Rossby waves. These waves were first described by the Swedish-American meteorologist Carl Gustaf Rossby during the 1930s. Rossby waves arise because of the way Earth's rotation varies with latitude. As air moves north or south, changes in the Coriolis effect create slow, meandering waves in the upper-level winds. These waves can stretch across entire continents and oceans. Rossby waves are particularly important in shaping the behavior of the jet stream, a narrow band of fast-moving air found high in the atmosphere. The jet stream acts like a river of wind flowing around the planet. Its path is rarely straight. Instead, it forms large curves and loops influenced by Rossby waves. When the jet stream bends northward or southward, it can bring dramatic shifts in weather patterns. Cold polar air may plunge southward into lower latitudes, while warm air from the tropics can surge northward. These movements influence storms, heat waves, and prolonged weather patterns that affect millions of people. Despite the underlying physics guiding atmospheric motion, predicting the exact behavior of weather systems remains extremely challenging. One of the reasons for this difficulty became clear in the 1960s through the work of the American mathematician and meteorologist Edward Lorenz. Lorenz was studying simplified models of atmospheric circulation when he discovered something surprising. Tiny differences in the starting conditions of his calculations produced dramatically different results over time. This sensitivity to initial conditions became known as chaos theory. Lorenz illustrated the idea with a famous metaphor often called the butterfly effect. The phrase suggests that the flap of a butterfly's wings in one part of the world might eventually influence the formation of a storm somewhere else. The metaphor is not meant to be taken literally. A single butterfly cannot create a hurricane. Instead, the idea highlights how small variations in complex systems can grow and interact over time, making long-term predictions extremely difficult. In the atmosphere, countless small factors influence the evolution of weather patterns. Slight differences in temperature, humidity, or wind speed can gradually amplify as air masses interact. Because of this complexity, accurate weather forecasts typically become less reliable, beyond about a week or two. Despite these challenges, modern meteorology has made enormous progress thanks to advances in observation and computing. Today, vast networks of weather stations, satellites, radar systems, and atmospheric sensors collect data from across the globe. This information feeds into powerful computer models that simulate atmospheric behavior. One of the leading institutions in this field is the European Centre for Medium-Range Weather Forecasts, often abbreviated as ECMWF. Based in Europe but serving scientists worldwide, this research centre operates some of the most advanced climate and weather models ever developed. Using supercomputers, the ECMWF processes vast amounts of atmospheric data to produce forecasts and long-term climate simulations. These models attempt to capture the complex interactions between the atmosphere, oceans, land surfaces, and ice sheets. Although no model can perfectly predict the future, these systems provide increasingly accurate insights into how Earth's atmosphere behaves. What emerges from all of this research is a picture of a planet wrapped in a constantly moving ocean of air. Warm air rises near the equator, cold air sinks near the poles, winds sweep across continents and oceans, guided by the rotation of the planet and shaped by the invisible architecture of atmospheric waves. Storms form, evolve, and fade as energy flows through this dynamic system. From the calm of a quiet evening to the swirling power of a hurricane, the atmosphere is never truly still. It is another layer of motion surrounding a planet where nearly every system, from the deepest core to the highest clouds, is in constant movement. As Earth continues its steady journey around the Sun, another subtle feature of the planet's motion quietly shapes the rhythms of life across its surface. This feature is the tilt of Earth's rotational axis. If you imagine the Earth spinning like a top, you might picture the axis pointing straight up and down relative to the plane of its orbit around the Sun. But in reality, the axis is not upright. Instead, it is tilted. Earth's rotational axis leans at an angle of about 23.5 degrees relative to the plane in which the planet orbits the Sun. This plane is known as the ecliptic plane. This tilt may seem like a small detail, but it has enormous consequences. Without it, the climate and rhythms of the planet would be dramatically different. As Earth travels around the Sun over the course of a year, the tilted axis maintains nearly the same orientation in space. This means that during part of the orbit, the northern hemisphere leans toward the Sun, while the southern hemisphere leans away. 6 months later, the situation reverses. The southern hemisphere tilts toward the Sun, while the northern hemisphere angles away. This shifting orientation changes the way sunlight reaches different parts of the planet. When a hemisphere tilts toward the Sun, sunlight arrives more directly and for longer portions of the day. The Sun climbs higher in the sky, and daylight hours become longer. These conditions create summer. When a hemisphere tilts away from the Sun, sunlight arrives at a lower angle and spreads over a larger area. The Sun appears lower in the sky, and daylight hours grow shorter. These conditions produce winter. The difference in sunlight angle is more important than the distance between Earth and the Sun. In fact, Earth is slightly closer to the Sun during the northern hemisphere's winter than during its summer. The seasonal temperature changes are driven primarily by the tilt of the planet, not by variations in orbital distance. During the equinoxes, which occur around March and September, Earth's axis points sideways relative to the Sun. At these moments, Both hemispheres receive nearly equal amounts of sunlight, and day and night last roughly the same length across the globe. At the solstices, the tilt reaches its most extreme orientation relative to the Sun. The June solstice brings the longest day of the year in the Northern Hemisphere, while the December solstice produces the longest day in the Southern Hemisphere. These cycles repeat year after year as the planet continues its orbit. Although the tilt appears steady on human timescales, scientists have discovered that it changes slightly over much longer periods. One of the researchers who studied these variations in detail is the French planetary dynamicist Jacques Lascar. Lascar developed sophisticated mathematical models to analyze how gravitational interactions between planets influence Earth's axial tilt over tens of thousands and even millions of years. His calculations show that Earth's tilt does not remain perfectly fixed. Instead, it slowly oscillates between about 22 degrees and 24.5 degrees over a cycle lasting roughly 40,000 years. These gradual variations play a role in long-term climate changes on Earth and are connected to the orbital cycles studied in paleoclimate research. Even with these variations, Earth's tilt remains relatively stable compared with some other planets. A striking example of this contrast can be seen on Mars. Mars has an axial tilt that currently measures around 25 degrees, which is somewhat similar to Earth's. However, Mars lacks a large stabilizing moon, like the one orbiting Earth. Because of this, gravitational interactions with other planets can cause Mars's tilt to shift far more dramatically over time. Computer simulations suggest that the Martian axis may vary between roughly 15 degrees and more than 45 degrees over millions of years. Such large swings would produce extreme climate changes. At very high tilt angles, the poles of Mars could receive intense sunlight during summer, causing polar ice to melt and redistribute across the planet. At lower tilt angles, polar regions might remain permanently cold and dark. Earth avoids these wild fluctuations largely because of the stabilizing influence of the Moon. The Moon's gravitational pull helps keep Earth's axis from wandering too far from its current orientation. In this way, the Earth-Moon system quietly contributes to the long-term stability of the planet's climate. The presence of seasons also shapes the living world in countless ways. Plants respond to seasonal changes in sunlight and temperature. Many species grow leaves, flower, and produce seeds according to the annual cycle of daylight. Animals have also evolved behaviors synchronized with the seasons. Birds migrate across continents following shifting temperatures and food supplies. Many mammals enter periods of hibernation during colder months when resources become scarce. Even microscopic organisms in oceans and lakes respond to seasonal changes in light and temperature, creating cycles of growth that influence entire ecosystems. Humans, too, live within these rhythms. Agricultural systems depend heavily on seasonal timing. Crops are planted and harvested according to patterns of sunlight, rainfall, and temperature that repeat year after year. Across cultures and centuries, seasonal changes have shaped festivals, calendars, and traditions. All of this emerges from a simple geometric fact. The axis of Earth is tilted as the planet moves through space. That tilt causes sunlight to fall unevenly across the planet during its yearly orbit. The result is the familiar rhythm of spring, summer, autumn, and winter. What might seem like a quiet detail of planetary orientation is actually one of the most influential motions affecting life on Earth. The steady lean of the planet's axis creates a cycle that touches every ecosystem, guiding biological rhythms and shaping the climates of continents and oceans alike. And like so many other motions of the Earth, it unfolds quietly, repeating year after year as the planet continues its journey around the Sun. If Earth were a perfectly rigid sphere spinning in complete isolation, its rotational axis would remain fixed in the same direction forever. But the real planet is more complicated. Earth is not perfectly rigid. It is made of shifting continents, circulating oceans, flowing mantle rock, and a molten outer core. In addition, the planet exists within a gravitational environment shaped by the Sun and Moon. Because of these influences, the orientation of Earth's rotation is not perfectly stable. Instead, the axis performs a series of slow and subtle motions, each unfolding over different timescales. One of the most important of these motions is known as axial precession. Axial precession was first identified more than 2,000 years ago by the Greek astronomer Hipparchus, who lived during the 2nd century before the Common Era. Hipparchus carefully compared the positions of stars recorded by earlier astronomers with his own observations. Over time, he noticed a slight shift in the positions of stars relative to Earth's seasonal calendar. The change was small, but unmistakable. Hipparchus concluded that the orientation of Earth's rotational axis must be slowly drifting through space. Today we understand that axial precession occurs because Earth is not a perfect sphere. As we have seen, the planet bulges slightly at the equator due to its rotation. This equatorial bulge allows gravitational forces from the Sun and the Moon to exert a gentle torque on the planet. That torque causes Earth's axis to slowly trace a circular path through space, somewhat like the wobble of a spinning top as it begins to tilt. This motion unfolds extremely slowly. One complete cycle of axial precession takes about 26,000 years. Because of this gradual shift, the direction that Earth's axis points toward in the sky changes over long periods of time. At present, the axis points roughly toward the star Polaris, often called the North Star. But several thousand years ago, a different star occupied that position. Thousands of years in the future, the axis will point toward yet another star. To human observers living within a single lifetime, this change is almost imperceptible. Yet over long stretches of history it becomes clearly measurable. Axial precession is only one of several small variations in Earth's rotation. Another subtle motion is known as the Chandler wobble. This phenomenon was discovered in the late 19th century by the American astronomer Seth Carlo Chandler. Chandler studied precise measurements of Earth's rotational axis and noticed that it does not remain perfectly fixed relative to the surface of the planet. Instead, the axis shifts slightly over time, tracing a small irregular circle. The Chandler wobble has a period of about 433 days, or a little more than 1 year. The motion is extremely small. The axis moves by only a few meters relative to Earth's surface. Yet with modern instruments, even such tiny changes can be detected and studied. The Chandler wobble occurs because Earth is not perfectly rigid. The movement of air in the atmosphere, the circulation of ocean currents, and changes within the mantle all influence the distribution of mass across the planet. When mass shifts, the rotation of the planet responds accordingly. Imagine a spinning figure skater holding weights in their hands. If the skater shifts the weights slightly, the balance of the spin changes. A similar principle applies to Earth. When large amounts of mass move across the planet, the rotational axis adjusts slightly to maintain balance. In recent years, scientists have also studied how modern environmental changes influence Earth's rotation. One example involves the melting of large ice sheets in regions such as Greenland and Antarctica. As glaciers melt, enormous volumes of water move from land into the oceans. This redistribution of mass alters the way weight is distributed across the planet. Geophysicists have found that such changes can shift Earth's rotational axis by small but measurable amounts. The effect is subtle, but it demonstrates how sensitive planetary rotation can be to changes occurring at the surface. Tracking these variations requires extremely precise measurements. One organization responsible for coordinating this work is the International Earth Rotation and Reference System Service, commonly abbreviated as IERS. The IERS gathers data from observatories around the world, including satellite measurements, radio telescope observations, and laser ranging experiments. These observations allow scientists to monitor the orientation of Earth's rotation with remarkable precision, often down to fractions of a millisecond in the length of a day, or tiny shifts in the axis position. Through these measurements, researchers maintain an accurate global reference system used for navigation, satellite operations, and space exploration. Beyond these short-term variations, Earth may experience an even slower and more dramatic type of motion known as true polar wander. True polar wander occurs when the entire outer shell of the planet gradually shifts relative to the rotational axis. In this scenario, the geographic positions of the poles change because the distribution of mass within the planet evolves over geological time. For example, if large regions of mantle rock become unusually dense or buoyant, the planet may slowly reorient itself so that mass is redistributed more evenly around the axis of rotation. Unlike plate tectonics, which moves individual continents relative to one another, true polar wander involves the rotation of the entire crust and mantle together. Evidence for this phenomenon comes from geological records showing that ancient magnetic orientations in rocks sometimes differ from what would be expected if only plate motion had occurred. Although true polar wander unfolds extremely slowly, typically over millions of years, it provides another reminder that Earth's orientation in space is not absolutely fixed. Instead, the planet's rotation responds to forces both within and beyond its surface. Taken together, these subtle motions reveal a deeper truth. The axis of Earth is not a rigid pointer frozen in place. It is part of a dynamic system influenced by gravitational forces, shifting mass within the planet, and the ongoing evolution of Earth's interior. From the slow sweep of axial precession to the delicate dance of the Chandler wobble, the planet's rotation contains layers of motion that are almost invisible in daily life. Yet these quiet adjustments are another example of how Earth refuses to remain completely still, even in the way it spins through space. If we step back and look at Earth's journey around the Sun over very long periods of time, another layer of motion gradually comes into view. The orbit itself is not perfectly constant. The shape of the orbit shifts slowly. The tilt of the planet's axis changes slightly. Even the timing of Earth's seasons drifts relative to the position of the orbit. These variations are extremely slow, unfolding over tens of thousands and sometimes hundreds of thousands of years. Yet despite their gentle pace, they have played a major role in shaping the climate history of our planet. The scientist who first calculated these patterns in detail was the Serbian mathematician and geophysicist Milutin Milankovic. During the early 20th century, Milankovic studied how variations in Earth's orbit affect the amount of solar radiation reaching different parts of the planet. His work built upon earlier ideas proposed by 19th century scientists such as James Kroll, but Milankovic developed the theory with much greater mathematical precision. He calculated how long-term changes in Earth's orbit influence the distribution of sunlight across latitudes and seasons. These patterns of orbital variation are now known as Milankovic cycles. Milankovic identified three main types of orbital change that influence the climate system. The first involves the shape of Earth's orbit, a property known as orbital eccentricity. Although Earth's orbit is often described as circular, it is actually a slightly elongated ellipse. The degree of that elongation changes slowly over time due to gravitational interactions with other planets, particularly Jupiter and Saturn. During periods of low eccentricity, Earth's orbit becomes more circular. During periods of higher eccentricity, the orbit becomes slightly more stretched. These variations follow cycles lasting roughly 100,000 years and 400,000 years. Even at its most elongated, Earth's orbit remains only mildly elliptical, but the changes subtly affect how solar energy is distributed across the seasons. The second orbital variation involves the tilt of Earth's axis, sometimes called obliquity. As we've seen, the planet's axis currently leans at about 23.5 degrees relative to the plane of its orbit. However, this tilt does not remain perfectly constant. Over a cycle lasting roughly 40,000 years, the tilt slowly varies between about 22 degrees and 24.5 degrees. When the tilt increases, seasonal contrast becomes stronger. Summers grow warmer and winters become colder, especially at higher latitudes. When the tilt decreases, seasonal differences become more moderate. These changes influence how much sunlight reaches polar regions during summer months, which can affect the growth or melting of large ice sheets. The third component of Milankovic cycles involves the timing of Earth's seasons relative to its orbit, a motion linked to axial precession. As the axis slowly wobbles over a cycle of about 26,000 years, the orientation of Earth during different points in its orbit gradually shifts. This means that the timing of seasons relative to Earth's closest approach to the Sun, called perihelion, slowly changes. At present, Earth reaches perihelion during early January, which means the Northern Hemisphere experiences winter while the planet is slightly closer to the Sun. Thousands of years from now, the timing will reverse. Precession therefore alters the seasonal contrast between hemispheres, affecting how sunlight is distributed across the planet. Each of these orbital variations is subtle on its own, but when they combine, their effects can become powerful. Milankovic proposed that these cycles influence the growth and retreat of massive continental ice sheets during Earth's ice ages. During certain combinations of orbital conditions, summer sunlight at high northern latitudes becomes weaker. When summers are cool enough, winter snow fails to melt completely. Over time, snow accumulates, gradually compacting into glaciers and expanding ice sheets. Conversely, when orbital conditions increase summer sunlight in these regions, ice sheets begin to melt and retreat. Milankovic's theory remained controversial for several decades after it was first proposed. Although the mathematics appeared sound, scientists lacked sufficient geological evidence to confirm that orbital cycles truly matched Earth's climate history. The breakthrough came during the 1970s through the work of the American climate scientist John Imbrey and his colleagues. Imbrey studied sediment cores extracted from the deep ocean floor. These cores contain microscopic shells of marine organisms that lived thousands and millions of years ago. By analysing variations in oxygen isotopes within these shells, scientists can estimate past ocean temperatures and ice volumes. When Imbrey and his collaborators examined these records, they discovered patterns that closely matched the timing predicted by Milankovitch cycles. The growth and retreat of ice sheets appeared to follow the rhythms of Earth's orbital variations. These findings provided strong confirmation that subtle changes in Earth's orbit can influence global climate. Much of the data supporting this work came from large-scale ocean drilling projects, where research vessels recovered sediment cores from deep beneath the ocean floor. Programs such as the Deep Sea Drilling Project and its successors helped build an extensive archive of Earth's climate history stretching back millions of years. Today, scientists continue to study these long-term climate patterns using advanced models and observational data. One major research centre involved in this work is the NASA Goddard Institute for Space Studies in New York. Researchers at this institute use sophisticated climate models to explore how variations in orbital geometry interact with atmospheric composition, ocean circulation, and ice sheets. Their work helps scientists understand how Earth's climate system responds to both natural cycles and modern human influences. Milankovitch cycles do not operate in isolation. They interact with many other processes within the Earth system, including volcanic activity, ocean circulation, and greenhouse gas concentrations. But the cycles provide a kind of slow background rhythm for Earth's climate, a steady pulse driven by the mechanics of celestial motion. Over tens of thousands of years, these orbital variations gently alter the amount and distribution of sunlight reaching the planet. The result is a climate system that slowly shifts between colder and warmer phases. Ice sheets grow, glaciers advance, and later they retreat again as conditions change. All of this unfolds because the path of Earth around the Sun is not perfectly fixed. Even the orbit itself participates in the ongoing dance of motion that defines our planet's place in the solar system. By this point, a pattern begins to emerge. Earth is not defined by a single type of motion. Instead, it contains many layers of movement unfolding at once. The crust drifts through plate tectonics. The mantle circulates with slow convection currents. Oceans transport heat across entire basins. Winds sweep through the atmosphere. The magnetic field shifts as molten metal churns deep within the core. Even the orbit of the planet and the orientation of its axis change slowly over time. All of these processes are connected. To understand how they influence one another, scientists often turn to a field known as complex systems science. Complex systems science studies systems that contain many interacting parts, where the behaviour of the whole cannot be fully understood by looking at individual pieces in isolation. Examples of complex systems appear in many areas of science. Ecosystems, economies, neural networks, and weather patterns all display complex interactions between many components. Earth itself is one of the most remarkable examples of such a system. Geologists, oceanographers, atmospheric scientists, and biologists now often describe the planet as an Earth system, a network of interacting spheres. These spheres include the lithosphere, which contains the solid crust and upper mantle, the hydrosphere, which includes oceans, rivers, and ice, the atmosphere, the envelope of gases surrounding the planet, and the biosphere, the collection of all living organisms. Energy and matter constantly move between these spheres. Heat flows upward from the interior of the planet through volcanic activity and tectonic motion. Solar radiation warms the surface and drives atmospheric circulation. Ocean currents redistribute heat across the globe. Living organisms alter the composition of the atmosphere through processes such as photosynthesis and respiration. The motion of one system often influences the behaviour of another. For example, changes in ocean circulation can alter atmospheric patterns, which in turn affect rainfall and vegetation. Shifts in vegetation can change the amount of carbon dioxide absorbed from the atmosphere, influencing climate. Over long periods of time, the slow drift of continents can reshape ocean currents, which then affect global temperature patterns. This intricate web of interactions led some scientists to consider an intriguing possibility. What if life itself plays an active role in regulating the environment of the planet? One of the researchers who explored this idea was the British scientist James Lovelock. In the 1970s, Lovelock proposed a concept known as the Gaia hypothesis. The Gaia hypothesis suggests that the biosphere, the atmosphere, the oceans, and the surface of Earth interact in ways that help maintain conditions favourable for life. Lovelock developed this idea while studying planetary atmospheres, including those of Mars and Venus. He noticed that Earth's atmosphere is chemically unusual compared with the atmospheres of those neighbouring planets. For example, Earth's atmosphere contains large amounts of oxygen and methane existing together. From a purely chemical perspective, these gases should react with one another and disappear relatively quickly, yet they remain present because biological processes constantly replenish them. Lovelock argued that life itself helps regulate the composition of the atmosphere and the stability of environmental conditions. The idea was further developed in collaboration with the American microbiologist Lynn Margulis, who studied the role of microorganisms in shaping Earth's environment. Margulis emphasized that microscopic life forms, including bacteria and algae, play a major role in global chemical cycles. These organisms influence the carbon cycle, nitrogen cycle, and oxygen balance of the atmosphere. Although the Gaia hypothesis originally sparked considerable debate, many scientists now accept that biological processes strongly influence planetary systems. The modern field of Earth system science studies these connections in detail. Researchers investigate how living organisms interact with geological and atmospheric processes through feedback loops that can stabilize or alter environmental conditions. For example, forests absorb carbon dioxide from the atmosphere, helping regulate greenhouse gas levels. Phytoplankton in the oceans produce oxygen and influence cloud formation through chemical emissions. Even soil microorganisms contribute to nutrient cycles that affect plant growth and ecosystem stability. Understanding these interactions requires powerful tools. Today, scientists use advanced computer models to simulate the behavior of the entire Earth system. These models combine data from atmospheric measurements, ocean observations, geological records, and biological studies. Large international research collaborations contribute to this work, including climate modelling groups supported by organisations such as the National Aeronautics and Space Administration, the European Centre for Medium-Range Weather Forecasts, and many national meteorological agencies. By integrating these data, scientists can explore how energy flows through the planet's systems and how different components interact over time. One important insight from this research is that motion plays a crucial role in maintaining Earth's stability. Without the circulation of the atmosphere and oceans, heat from the sun would accumulate unevenly across the planet. Tropical regions would grow far hotter, while polar areas would become far colder. Without plate tectonics, important chemical elements trapped within Earth's interior would not be recycled back to the surface through volcanic activity. Without biological activity, the atmosphere would gradually drift toward chemical states far less favourable for life. In other words, Earth remains habitable not because it is still, but because it is dynamic. Motion allows energy and matter to circulate through the planet's systems. This circulation helps regulate temperature, redistribute nutrients, and maintain the delicate balance that supports life. The image that emerges from modern science is that of a planet functioning almost like a living network. Not alive in the biological sense, but composed of countless interacting processes that continuously exchange energy and material. The shifting continents, the flowing oceans, the swirling atmosphere, and the activity of living organisms all participate in this system. Together they create a world that remains stable enough for life, yet constantly changing over geological time. What first appears to be motion in separate layers of the planet gradually reveals itself as a connected system. Every part of Earth influences the others, and through this intricate dance of motion and interaction, the planet maintains the conditions that allow life to persist on its surface. If we zoom out far enough from Earth, the scale of motion expands dramatically. The planet rotates once every day. It orbits the Sun once every year, but the Sun itself is not stationary within the universe. Our star, along with every planet, asteroid, and comet in the solar system, is travelling through space as part of a much larger journey. That journey takes place inside the Milky Way galaxy. The Milky Way is a spiral galaxy containing hundreds of billions of stars. Its structure resembles a vast rotating disk with spiral arms stretching outward from a dense central region. Our solar system resides within one of these spiral arms, often called the Orion Arm or the Orion Spur, a minor branch located between two larger spiral arms known as Sagittarius and Perseus. From our position inside the galaxy, the the night sky appears as a broad band of faint light stretching across the heavens. That glowing band is the combined light of enormous numbers of distant stars within the galactic disk. But the entire structure is in motion. Just as planets orbit stars, stars themselves orbit the center of their galaxy. The Sun travels around the center of the Milky Way at a speed of roughly 220 kilometers per second. That is about 800,000 kilometers per hour. Even at that tremendous speed, the galaxy is so vast that completing one full orbit takes an extraordinarily long time. Astronomers estimate that the solar system requires roughly 230 million years to circle the galactic center once. This period is sometimes called a galactic year. To place that in perspective, the dinosaurs lived on Earth during the last galactic orbit. When the solar system was last in roughly its current position around the galaxy, the earliest dinosaurs had not yet appeared. Understanding how stars move through the galaxy has been an important challenge for astronomers. One of the early pioneers in this field was the Dutch astronomer Jan Oort. In the 1920s, Oort studied the motions of nearby stars and discovered patterns indicating that the Milky Way rotates as a whole. His work helped demonstrate that stars closer to the galactic center orbit faster than those farther away. These observations provided some of the first quantitative insights into the structure and rotation of our galaxy. Oort also proposed the existence of a vast cloud of icy bodies surrounding the solar system at enormous distances, a region now known as the Oort cloud, which may serve as the source of many long-period comets. As astronomical observations improved, scientists began studying how the rotation of entire galaxies behaves. In the 1970s, the American astronomer Vera Rubin made a discovery that would profoundly change our understanding of the universe. Rubin studied the rotation curves of spiral galaxies by measuring how fast stars orbit at different distances from their galactic centers. According to Newtonian gravity, stars farther from the center of a galaxy should move more slowly than those closer in, because the gravitational pull weakens with distance. Instead, Rubin found that stars in the outer regions of galaxies were moving much faster than expected. The rotation curves remained nearly flat, meaning that stars far from the center were orbiting at speeds similar to those closer in. The only way to explain this motion was to assume that galaxies contain far more mass than can be seen in stars and gas alone. This unseen mass became known as dark matter. Dark matter does not emit or absorb light, which makes it invisible to telescopes. Yet its gravitational influence appears to shape the structure and motion of galaxies. Today, astronomers believe that dark matter forms vast halos surrounding galaxies, including the Milky Way. These halos contain several times more mass than the visible stars and gas combined. As the solar system travels through the Milky Way, it also performs another subtle motion. Instead of remaining perfectly within the thin disk of the galaxy, the solar system slowly oscillates above and below the galactic plane. This motion resembles the gentle up and down movement of a boat riding ocean swells. The cycle takes tens of millions of years to complete. During this time, the solar system drifts slightly above the plane of the galaxy, before gradually passing through it and moving to the opposite side. The cause of this motion lies in the gravitational pull of the galaxy's disk. Just as gravity pulls objects toward the surface of Earth, the mass within the galactic disk pulls stars toward the midplane of the galaxy. As stars move upward or downward relative to that plane, gravity gradually draws them back again, creating a slow oscillation. The consequences of this motion remain an active topic of research. Some scientists have speculated that passing through denser regions of the galactic plane might influence the solar system's environment by disturbing distant comet clouds or altering the flow of cosmic radiation. However, these ideas remain under investigation, and the precise effects are still being studied. In recent years, astronomers have gained an increasingly detailed view of the Milky Way thanks to ambitious space missions. One of the most important of these projects is the Gaia spacecraft, launched by the European Space Agency. Gaia is designed to measure the positions and motions of stars with extraordinary precision. By tracking tiny shifts in the positions of more than 1 billion stars, Gaia is creating the most detailed three-dimensional map of the galaxy ever assembled. These measurements allow astronomers to reconstruct the past movements of stars and predict how the galaxy will evolve in the future. Through Gaia's observations, scientists can study how spiral arms form, how star clusters disperse, and how the Milky Way interacts with neighboring galaxies. All of this research reinforces a remarkable realization. Even at the largest scale accessible to our experience, motion never stops. Earth spins beneath our feet. It orbits the Sun year after year. The solar system travels around the centre of the Milky Way, and the Milky Way itself moves through the vast cosmic web of the universe. The quiet night sky may appear still to the eye, but in reality our planet is part of an immense and ongoing journey through space. And every moment of our lives unfolds aboard a world that is travelling through the galaxy at extraordinary speed, carried along with billions of other stars in a vast cosmic orbit.